I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we'll see what is dropout and what is the purpose of learning this dropout in neural network. We'll see one by one. Before going into the dropout, all we should know about the topic overfitting. This we have seen it in the previous lecture. Overfitting occurs when a neural network learns the training data too well, including noise or random fluctuations. This means the model is not just learning the core patterns in the data, but also the noise and irregularities that don't generalize well. As a result, the neural network becomes too specific to the training data. The model performs the data. Next, the model performs very well on training data, but poorly on unseen data. The model performs very well on training data, but poorly on unseen data. That means because it memorizes training samples, the model achieves higher accuracy on that set, but it performs drops significantly when exposed to new unseen data. It memorizes rather than generalizes pattern. That means overfitting reflects a failure to extract general rules from the data. Instead of learning the logic behind the data, the network remembers exact example which limits adaptability. Next, symptoms of overfitting: high training accuracy, low test accuracy, large gap between training and validation losses. So this means that this is the most direct evidence of overfitting. The network becomes too tuned to train data and fails to make correct predictions on test data. And a large gap between training and validation losses means as training progresses, the loss on training set keeps decreasing, but validation loss stops decreasing or even increases, highlighting that the model is not generalizing. Next, it was caused by too many parameters and very few large or deep network can fit as any function, including noise, and excess parameters give it excessive freedom to learn unwanted patterns and too few training examples. With limited data, the model struggles to find common patterns, making it more likely to memorize the data set rather than generalize. And a lack of regularization. Without mechanism like dropout or L2 regularization, the model is free to overfit. Regularization techniques impose constraints that promote generalization. Next, why should we use dropout? Dropout, the purpose of using dropouts. The dropouts helps to reduce in overfitting in deep network. It introduces randomness by temporarily removing neurons during training, which prevents the model from becoming too dependent on any single path or pattern. It encourages network to learn robust and generalizes the features. Since neurons are randomly deactivated, the network is pushed to develop features that are useful regardless of which neurons are active, promoting broader understanding. Next, prevents a co-adaptation of neuron, that is, neurons relying on each other. It prevents a co-adaptation neurons relying on each other. Without dropout, certain neurons may only be effective when used together. Dropout disrupts these dependencies, encouraging each neuron to contribute independently. And it acts like training and as ensemble of many subnetworks. That means each forward pass effectively trains a different smaller network. At test time, their combined effect mimics the behavior of ensembles of models, improving robustness, and it adds randomness, making the model more resilient. The stochastic behavior during training creates diversity in the learned representations, reducing the chances of overfitting to specific features or data artifacts. Next, introduction to dropout. Dropouts randomly disables a subset of neurons during training. Means by randomly setting neuron outputs to zero during each iteration, the model structures changes dynamically, which serves an implicit regularizar. This makes each forward pass use a different subnetwork. Means each batch is processed by a unique configuration of active neurons, which prevents overfitting and ensures that no specific path dominates learning. During interference, all neurons are active. When making predictions, the model uses the full set of neurons without dropping any, ensuring consistent and complete use of learned features. And it improves generalization by encouraging redundant future learning. Since different subsets of neurons are active at different times, the network learns to duplicate or spread out important features across multiple neurons. And how dropout works with and we'll see to it in terms of equation. Each neuron is retained with the probability 1 minus p, and where p is the dropout rate. Binary mask Ri is sampled from the Bernoulli's distribution. So the first equation, it means each neuron has a fixed change of being turned off for a particular training step and controlling the strength of regularization. And the binary mask Ri is sampled from the Bernoulli's distribution. So it is given by Ri is equal to Bernoulli of 1 minus b, hi bar is equal to Ri into hi. And hi is the original neuron output, hi bar is the output layer, output after applying dropout, Ri is the dropout masks. So what it says, this mask determines whether each neuron is active. Active means the value is 1, inactive means the value is 0. At introducing the randomness in the network structure during training, and this is the equation. This is the actual activation used for backpropagation, which may be 0 if the neuron was dropped. And this Ri, what it says, dropout mask 0 or 1. This mask dictates which neurons are dropped. It regenerated for each training step and is not used during the inference. Next, dropout during interference. At a test time, we don't drop any neuron. Dropout is only used during training. When the model is deployed, all neurons are active to ensure stability and complete information flow. And to match expected activation level, and scales neuron outputs. Because only a fraction of neurons were active during training, we need to adjust the outputs during inference to maintain consistency in output magnitude. And two common approaches, train time scaling and test time scaling. In training time scaling, and the scales output is by 1 divided by 1 minus 1 divided by 1 minus p. And so the and test timing is given by 1 minus p. This we should understand well. Training time 1 divided by scale output 1 divided by 1 minus p. This is testing time signal scaling is 1 minus p. This equation adjusts the activation during inference. So the equation test time scaling hi bar is equal to 1 minus p into hi. So this equation adjusts the activation during the inference to reflect the reduced number of active neurons during training. It ensures that the total activation remains statistically similar. Next, intuition behind the dropout. Dropout prevents resilience on the specific neuron. By randomly disabling neurons, the network is discouraged from over specializing any part of the architecture, leading to more generalized behavior. And each training step uses a new subset of full model. The network effectively changes structure every iteration, which increases diversity in the paths used for learning. Next, more models behave like an ensemble for smaller networks. Each configuration represents a different subnetwork. The final model can be thought of as the average of many subnetworks, enhancing generalization. And it forces neurons to cooperate better and extract shared features. In the sense, no single neuron can dominate the learning process. So features must be distributed across the network, improving robustness and redundancy. Next, dropout is convolution layers, fully connected layers or convolution layers. In CNN, dropouts in a fully convolution layer. In CNN, dropout is used after pooling layer by or FC layers. That is, FC means fully connected layers. Most effective in dense. Dropout is particularly benefited in fully connected layers, and these common in MLPs and a dense layer of CNN. There are there are the layers where the risk of overfitting is high due to the dense interconnections, making dropout a practical choice. And it is so in this case, so here, so intuition behind this is dropout prevents the resilience on specific neurons. By randomly disabling neurons, the network is discouraged from over specializing any part of the architecture, leading to more generalized behavior. Each training step uses the new subset of full model. In the sense, the network effectively changes structure every iteration, which increases diversity in the path used for learning. And the model behaves like an ensemble of smaller network. Each configuration represents a different subset. The final model can be thought of as the average of many subnetworks, enhancing generalization. And it forces neurons to cooperate better and extract shared features. No single neuron can dominate the learning process, so features must be distributed across the network, improving robustness and redundancy. Next, dropout in fully connected layers. And the most effective in dense, that is fully connected layers, dropout is particularly. So here, so in this case, the most effective dense is common in MLP, and dense layers are of convolution neural network and is applied after the activation like ReLU functions. And here common in MLPs and dense layers of CNNs. And these are layers where the risk of overfitting is high due to the dense interconnection, making dropout practical choice. Next, applied after activation function in ReLU. Typically, dropout is used after applying activation function so that it tracks activated output, not the pre-activation values. And typical dropout rate is p is equal to zero point 0.5 for hidden layers and p is equal to zero point 0.2 for input layers. Lower dropout rates are used at the input because dropping too much information early in the network can degrade the performances. Next, dropout versus that is in the convolution layers. Here, the dropout versus other regularization techniques. Before that, this is the connected layers. Next, dropouts in the regularization, dropout versus other regularization techniques. In this case, the dropouts are stochastic, disables neurons during training, and the dropout works by randomly modifying the network during each pass, which acts as a powerful form of regularization. Next, L2 regularization adds penalty on large weights, means it reduces the overfitting by discouraging excessively large weight values, thus controlling model complexity. And early stopping means it halts training before overfitting worsens by monitoring validation loss and stopping when it starts to increase. This technique prevents the model from fitting noise in the later stages, and the dropout works well in combination with these methods. Each regularization method addresses overfitting differently, and using them together can produce more reliable and accurate models. Next, choosing dropout rate. Dropout rate is Dropout rate P is the hyperparameter. It defines the probability of dropping neurons and must be tuned based on the data set and architecture. And the typical values input layer here we are considering P is equal to 0.1 to zero point 0.3, hidden layer P is equal to zero point 0.5. Smaller dropout rates are used for input layer to avoid discarding too much raw information early on. And hidden layer zero point 0.5 we are fixing. This is the standard rate for most hidden layers in practice. It provides good balance between model robustness and train stability. And too high for underfitting. Dropping too many neurons can make the neuron network ineffective at learning, leading to poor performance on both training and testing data. Next, too low will gives us weak regularization. If a dropout is too rare, it may not sufficiently prevent overfitting, especially in deep networks with many parameters. And use validation data tune. Optimal dropout rate vary. Validation performance should guide selection to avoid both under and overfitting. Coming into the summary, Dropout is a simple and a powerful tool to reduce overfitting. Its ease of implementation and effectiveness make it a go-to technique for improving generalization in deep learning model, and it encourages diversity in learned parameters. By randomly disrupting pathways, Dropout ensures that multiple features represent each concept, improving redundancy and flexibility. Approximates model averaging at low cost. Instead of training many separate models, Dropout simulates an ensemble effect within a single model, offering high performance with lower computational demand. And it is widely used in deep learning models, including CNN, RNNs, and transformers. That means its versatility has made it a standard component in a wide range of architectures across different types of data and tasks. So that's all about this dropout in the neural networks. Hope everyone enjoyed about this dropout topic. Thank you.